Good afternoon, everyone, and thank you for joining us here. As already said, my name is Kaiko Kivi. I'm a third-year PhD candidate at the Estonian Academy of Arts, and my supervisor is Dr. Rene Puusepp, who is also here and presenting later. Productivity growth and affordable housing have long been challenges for have long been challenges for the ASC sector. Modular construction and using prefabricated components promises efficiency and scalability, but faces low adoption. Digitalization has helped streamline processes, yet we still haven't fully achieved affordable mass customized housing at scale. Expected productivity growth in construction. So the images here are actually building systems from 100 years ago, and the expectation to a better and higher quality mass housing was also already there back then, coming with the industrialization. So my research aims to identify key challenges in designing for modular construction and building systems. By understanding these challenges, we can develop better digital tools for architects, bridging gaps between design, manufacturing, and digital workflows. One of the common issues here is integrating data across design tools and stages for the building design. A major challenge for manufacturers' workflows is quickly and accurately responding to architectural proposals within digital and regulatory constraints. Aligning proposals with production and supply chain processes remains difficult. Digital tools can help better integrate and streamline design to production workflows and feedback. So my research uses creative practice-based research approach, prototyping workflows that combine industry observation and my experience as a computational tool development and designer. The focus is on how architects can engage with modular systems, recognizing space as a central architectural intent. So the earlier projects that I've done with digital information and modeling have involved energy efficiency computation and housing configurations, which has led me to question how can architectural involvement with very diverse spatial expectations be integrated into the process. So in this case, we need to integrate a diverse set of information systems, from design intent to manufacturing to operations to reuse and circular life of materials, and etc., and building operations and so on. Seamless workflows require integrated relational data models, but conventional building information model focus on geometry and hierarchy, and this causes issues when combining spatial models. So my question is, could spatial configuration itself be the platform for BIM and manufacturing integration? Looking at the early process of developing design tools, digital design tools. These tools were developed to offer computational assistance with geometry and etc. analysis. But today's conventional BIM tools mostly replicate traditional drawing and manual modeling of buildings. So my research aims to empower architects to model the abstract configuration of space as a digital entity model, making it easier to iterate and bridge the construction and fabrication models. To create a domain-agnostic spatial model, I used the topologic pi library for spatial reasoning. This enables composing geometry and attaching semantic information, allowing extraction and linking of building entities for generating construction data and further detailing in building information models and manufacturing models. So now I will jump to an example research projects that we did last year and the beginning of this year with the research team at PAK. Elementaarne Koda, sorry, develops a building system utilizing CLT timber offcuts. And I will demonstrate how agile digital workflows and modularity can support implementing sustainable and efficient solutions. So the system itself uses offcuts as standardized elements in the grid. A parametric model lets us generate designs within these grid constraints. Then we created and analyzed several variants for further detailing. And then we chose one, and the model is then decomposed based on topology, using topologic methods to analyze and automate the building structure. So every spatial member is uniquely identified and remains linked to its topologic entity, improving data management and coordination. Model entities collect attributes about their edges and angles, enriching the model for deeper analysis and fabrication. So here the angles between the faces are defined as metadata in these contours for the panels. And as the next step, these panel models are then generated from this metadata, allowing for independent detailing and fabrication of these panels. Manufacturers' automation could handle this task through online services, for example, so that when the architect, for example, details this spatial model, it can get the exact details from the manufacturer instead of specifying and modeling it himself. And together with that, you would be provided information about cost, emissions, and for example, even production timelines and detailed models further on. In the next autonomous intervention, architects can specify windows, doors, openings, and regions for these CLT offcuts, addressing architectural intent and material details even further. So this demonstrates the importance of architects' involvement in the process and similarly engineers' involvement, being able to adjust the design. So eventually the detailed panels are then reintegrated into the 3D model, making it efficient to explore design solutions through this system, because the process I have shown could take just minutes to iterate over different designs. And also, going through this constraint system, it is easy to validate the design for manufacturing in real time. So you will always know that these elements will be manufacturable. So the conclusions that I'm trying to reach is that if this process would be fast and allow architects to iterate over designs that are flexible and not constrained so much to what manufacturers set out as, so that you can take these pieces or not and use ready-made solutions, but instead you can iterate over the system itself, over the possible outcomes spatially. And I will quickly show another example based on a 3-cycle building system, which is like quite like this frame here. This is the older version of it. So imagine architect just drawing these boxes or rectangles to define where the modules are. The manufacturer systems would respond with the frame. And as a next step, you would get all the necessary structural details into your model, and then you would be able to define the sections or divide it into rooms with the structure. And the next step, draw some windows and doors simply. And as a topological model, it will recognize how the rooms are connected through doors and how the walls and elements are connected with each other, what is the external shell and what are internal walls. And this allows for a manufacturing model to be instantly created in the process. And then with further detailing, you would pretty much get a ready-made building, so to speak. And just to remind you, this is the input that the architects would be required to do, to iterate over many models. So, thank you, and I'm open to questions.